All right, guys, we are on to section 2.2, normal distributions. So it says a normal distribution is described by a normal density curve, which looks like this right here. Okay, it looks like a bell curve. All right, any particular normal distribution is completely specified by two numbers, its mean and its standard deviation. The mean of a normal distribution is at the center of a symmetric normal curve. The standard deviation is the distance from the center to the change of curvature points on either side. Okay, we abbreviate the normal distribution with mean mu and standard deviation sigma as n. N stands for normal, and then we give the values of the mean and the standard deviation. So let me give you an example of a distribution that we know is normally distributed. So let's say we want to think about IQ, the variable IQ. Okay, so for IQ, the mean IQ for people falls right down the center of that symmetric normal distribution. The mean is 100, so the mean goes down the center. So 100 points is the mean. Okay. Now, we also know for IQ that the standard deviation is about 16 points. So if you look at these change of curvature points, okay, if you think about calculus, here we're concave down. When it switches to concave up, that's where one standard deviation is. And same thing over here. When it switches from concave down to concave up, that's a change of curvature. Okay, instead of down like a frown, it's up like a cup. So this distance right here is one standard deviation. All right, so that spread is 16 more. Okay, so if you go up by one standard deviation, we would go up to 116, and if you go down a standard deviation, you're at 84. Okay. So that's one standard deviation. So on the bottom, we put the IQ score. And the way we would abbreviate this, we would say, okay, IQ is a normal distribution, so we would write a capital N, and then we would tell the reader that the mean is 100 and the standard deviation is 16. That communicates to the reader that this is a normal distribution with a center point of 100 and a spread of 16. And then if we went one more standard deviation, if we went another 16 units, we would be out. Now we're two standard deviations. Okay. So we would go another 16 here. So if we went another 16, we would be up to 132 for an IQ. If we went down 16 more, okay, we would be down to, what's that, 68. Okay, and you can go another standard, you can go as many standard deviations as you want. The point here is this normal curve, it always has area. There's always a little bit of area. But the further you go out, less area is there. So if we went out another 16, we would be up to 148. And if we went down another 16 this way, we would be down to 52. Okay, we would be down to 52. So why do we use normal curves and why are they so powerful? Well, we'll talk about that next. All right, normal distributions are good descriptions for some distributions of real data, like IQ, okay, or heights of people. Normal distributions are good approximations to the results of many kinds of chance outcomes. We'll talk about that more when we get to the inference section of statistics. Okay. And then that's another talking about inference procedures. We need normal curves to do inference procedures, and we'll talk about that later. All right. So what's so special about this normal distribution, or this normal curve? Here's what's special about it. if we know a distribution is normal or approximately normal, okay, let me draw another normal curve. Okay, so if this is my mean, all right, and if I go out one standard deviation, one above and one below, this part of the graph right here, there's about 68% of people fall within one standard deviation. And this is a symmetric curve, okay? So within that, if 68% fall within one standard deviation, okay, so this is like, if this is your mean, this is 1 sigma, and this is -1 sigma, all right? Since it's symmetric, 34% of data falls in each half right here. Because if it's 68 total and it's symmetric, 34% fall between here and here and here and here. Now, what happens if you go out 2 standard deviations? 2 sigma and -2 sigma. Okay, if you go out to 2 standard deviations, not exactly, but about 95% of data falls within 2 standard deviations. So what does that mean? This amount right here, since it's symmetric, okay, each of those would be about 47.5%. What does that let me know? Well, if this part is 34, if that distance is 34%, or if that area is 34%, but this total area is about 47.5%, then just in this little region, if I subtract these two from each other, 47.5 minus 34, about 13.5% would actually just fall in this region. And there's another 13.5% over here as well. Okay. Now, if we go out 3 standard deviations by this empirical rule, okay, if we go out 3 standard deviations, we almost get everybody. We almost get everybody. That's about 99.7%. Okay. It's almost everybody. So this distance right here, from here to here, half of 99.7 would be 49.85%. And this is another 49.5, or 49.85, excuse me, roughly. Because the curve's symmetric. All right, well, if this amount was 47.5 and that amount is 49.85, then there's only about 2.35% just in this region. And there's 2.35% of people would be in this region. Okay. So we can just do those calculations real easily. And what's left over, if 99.7, there's only 0.3% left, and then that's equally distributed among the remaining parts. So if we go out further than 3 standard deviations, there's only 0.15% further than 3 standard deviations. So to the right of that or to the left of that. Only makes up 0.15%. All right, so here's a picture of it. Within 1 standard deviation, 68, within 2, 95, and within 3, 99.7. All right. Now this is a special normal curve. This is actually called the standard normal curve. And what makes it standard? A standard normal curve has a mean of 0, and just the standard deviation here equals 1. That's what makes it standard normal, and you'll see why that's important. Now, what is this? This is one standard deviation. So these numbers right here, these actually represent, okay, all of these numbers here. Since it's a standard normal curve, this is one standard deviation to the right. That's 2, that's 3. This is 1 to the left, 2 to the left, 3 to the left. So on a standard normal curve, these things are really z-scores. That's what they are. They're z-scores. Let's look at an example. It says the distribution of heights of adult American men is approximately normal, with a mean of 69 inches and a standard deviation of 2.5 inches. So if I was going to write this in short form, I would say, okay, the curve is normal, so I put a capital M, then parenthesis, and I would say mean of 69 inches and a standard deviation of 2.5 inches. Okay. Part A, draw a normal curve on which this mean and standard deviation are correctly located up to 3 standard deviations away. So let's draw our normal curve. Here's the mean. So this value is 69. If we go out 1 standard deviation, where the curve changes from concave down to concave up, you would have to add this distance. This is 1 standard deviation. So you would have to go 2.5 inches more than that. So that would put us up to 71.5. Then if you go 2.5 more, okay, you would be here. You'd be 2 standard deviations. So take 71.5 plus 2.5. So you would be up to 74 inches. All right, and then if you went 1 more standard deviation, you would be up to 76.5. I keep adding 2.5 each time. Now what about on the negative side? Okay, on the left side. That's 1 standard deviation to the left. So you start at 69, but you're going to the left. That's also 2.5. 69 minus 2.5 is 66.5. All right, go 2.5 more. That would put you down to 64. Go 2.5 more the other way. That's 61.5. So what does this mean? All right, if this curve is if this distribution is approximately normal, then 68% of men have heights between, what's 1 standard deviation? 66.5 and 71.5. Between 66.5 and 71.5 inches. All right, if we go out 2 standard deviations each way, then we can say that 95% of men have heights between 64 and 74 inches. If you want to know how tall this is just a tad under 6 feet. This is 5'6" and a half. 5'6.5", 5'11.5". This is 5'4" to 6'2". All right, and if we go 3 standard deviations, we can say that 99.7% of men have heights between 61.5 and 76.5 inches. Okay, so this is 5'1.5", and this is 6'4.5", because there's 12 inches in a foot. Okay. All right. So let's read the question. It says, what percent of men are taller than 74 inches? So what they want to know is they want to know what the area is to the right of there, if it's taller than 74. Well, since this curve is symmetric, this part is 50%, And we already talked about, okay, in here, we said that there's 34% of the data. All right, and in that next little section, all right, this little section, there's 13.5. All right, so just take 50 minus 34 minus 13.5 and you would get this amount. Okay, I'm just trying to kind of do that in my head. These two add up to 37 and a half. Or no, 47 and a half, sorry. Those add up to 47 and a half. 50 minus 47 and a half. This area to the right of there would just be 2.5%. Only 2.5% of men are taller than 6 feet 2, or 74 inches. It says, between what heights do the middle 95% of men fall? Well, that's between two standard deviations. That's this part. The middle 95% of men have heights between 64 and 74 inches. What percent of men are shorter than 66 and a half? Well, here's where 66 and a half is. That's at one standard deviation below. So this is 34%. Okay. So the percent of men that are shorter than that, just like before, the area to the left from the mean, that's 50%. So if you were to take this bottom half, which is half of the data, 50%, and subtract off this 34%, you would get that part. Those are the men that are shorter than 66 and a half. So what plus 34 equals 50? Well, it's 16. 16% of men are shorter than 66 and a half inches. That's 5 foot 6 and a half inches. All right. And question D, it says a height of 71 and a half inches corresponds to what percentile? All right, so here's where the 71 and a half is. We know that 50% of the data are less than 69. So we're already up to 50. Now to get up to this part, you need to add in another 34%. So 50 plus 34 would be 84. So that's 84%. All right, so let's keep going here. The standard normal distribution, we talked about what that was. This is an example of the standard normal distribution where the mean is 0 and the standard deviation is 1. Okay. All right. If a variable x has any normal distribution, just like IQ, with mean mu and standard deviation sigma, then we can standardize those numbers by turning the values into z-scores. And then it becomes a standard normal distribution. Okay. Now, I'm not going to read all this to you, but there's a table in the back of your book, I think it's in table A, where it lists these standard normal probabilities. So I'll show you how to interpret this. So let's say you have some person that has an IQ of, or has an IQ that corresponds to a z-value of negative, let's say that this value here is negative 2.34. What this table does for you, it tells you what the area to the left is of that. Okay. So if you go to negative 2.3 on the chart and follow it over until you get to the 0.04, it's like you're taking negative 2.3 and putting on another negative 0.04. That's 0.0096. So if that person had a z-score of negative 2.34, then the area to the left of that is really small. less than 1%. Okay? So that would be the area there. So it gives you a whole bunch of different z values all the way up to z-scores of negative 3.49. And on the next part, on the next page, all right, the first page is all about negative z-scores. The next page is what about if I have positive z-scores? Okay. So here, if this person had a z-score of 1.02, for instance, okay, if I look up 1.02, here's 1.0, then I have to go to here to the 0.8461 because it's under the 0.02. Okay, so that means that this area, okay, that area would be 0.8461. That means that this person that has a z-score of 1.02, they're in the 84.61 percentile. That means that their IQ is higher than 84% of all other people. So these tables are beneficial. But to be able to use these tables, you have to turn a normal distribution into a standard normal distribution. So you would have to know that, okay, if these are the IQ scores, what are the z-scores? Well, this person would have a z-score of, you do 100 minus 100, which is 0 over 16. So this would have a z-score of 0. The means always has a z-score of 0. That would have a z-score of 1. That would have a z-score of 2. That would have a z-score of 3. This would have a z-score of negative 1. That would have a z-score of negative 2. That would have a z-score of negative 3. And by turning data into z-scores, then we can use those tables. But there is an easier way, which we'll talk about. We can also use our calculator to help us. Our calculator has this standard normal table stored in it. Okay. So in this example, it says for the following exercises, use table A to find the proportional observations from the standard normal distribution that satisfies each of the following statements. In each case, sketch a standard normal curve and shade the area under the curve that is the answer to the question. And then use our calculator to check our answers. So in this first problem, they want to know what proportion of people have z-scores less than 2.85. Okay, so I'm going to draw a normal curve, a bell curve. I'm going to put a dashed line where the mean is. That has a z-score of 0 always on a standard normal table. Okay, here's one standard deviation above. Here's two standard deviations above. Okay. If this is where 3 standard deviations is above, 2.85 would fall pretty close to that. So these, remember, on a standard normal table, those are z-scores. They want to know less than 2.85. So I'm going to shade all the area that have z-scores less than 2.85. Okay. And then I'm going to use my table. All right. I'm going to use my table to answer the question. Okay. So I'm going to find 2.8 on the table, and I'm going to go under until I get to the 5. Okay. So someone with a z-score of 2.85, the area to the left of that, okay, equals 0.9978. So 99.78% of people have a z-score less than 2.85. Now the next question's a little bit difficult. Okay, let's think about what this one's saying. Okay, the z-score they give me is negative 1.66. So I'm just going to assume I know where that is, roughly. Okay, it's negative, which means it's to the left of the mean, which has a z-score of 0. But here they give me a greater than sign. Okay, so they actually want me to find this area. They want me to find the area to the right. Well, there's a problem with that. If I look on my tables, the tables give me the area to the left, not the area to the right. So here's the catch, okay? The area to the right and the area to the left combine to make 1, because the area under any density curve is always 1. Okay, so the way I'm going to find this, okay, what I'm actually going to do is I'm going to find this blue area using the table, and I'm going to subtract that from 1. So I'm going to do 1 minus, now I can look at my table. All right, I'm going to look at my table. Negative 1.66, here's negative 1.6, 0, 1, 2, 3, 4, 5, 6. Point 0.0485. So again, this blue area is the 0.0485 from the table. I have to subtract that from 1 because I want the area to the right. So if I do that, I get 0.9515. And we will check these on the calculator. I'll show you how you can do that fairly easily. The next one, z is greater than 2.46. So here's a z-score of 0 right down the middle. 2.46 would be over here. It would be to the right. Now, the question's asking me to find an area greater than that. So I'm trying to find this area. Again, my table won't tell me that. My table will only tell me this area. It will only give me a left area. So to figure out what the blue equals, I have to take 1 minus the red area. And the table gives me the red area. So going back into the table, a z value of 2.46, I believe. Yep, 2.46. Here's 2.4, 0, 1, 2, 3, 4, 5, 6. 0.9931. 1 minus that red area, which is 0.9931. So the area to the right of that, it would be 0.0069. All right. Next one's the hardest one. All right. So if I draw in this next one, there's my bell curve. Right here is a z-score of 0. The two z-scores I have here are 0.89. So let's say that a z-score of 0.89 falls about right there. And this one's negative 1.27. So maybe about right here. They want to know what percentage of people have z-scores between these two. So I want to know that area in blue. Well, the only way I can do this using my table is I have to find the area to the left. Okay, if I take this red area, just try to stay with me here for a minute. If I take this red area, the area to the left of a z-score of 0.89, and subtract off this part, then I can get the answer. I need to take that red area, the total red area that was there, and subtract off the green area to get the part I want. Okay. So if I look at my table, here, the area to the right of 0.89 is this, 0.8133. Yep, 0.8133. So red area, 0.8133. And I have to subtract off that green area. So that is the area to the left of a z-score of negative 1.27. So a z-score of negative 1.201234567 is 0.1020. So if I subtract those from each other, okay, that would be 0.7113, I believe. And that was this area. That was this blue area. That was the whole goal, to get that blue area. Okay. So that is how you find these probabilities using z-scores and using the tables. But of course, there's an easier way. That easier way is your calculator. So let me show you how we can do this. In each of these examples, these were all standard normal curves. Has a mean of 0 and an assumed standard deviation of 1. Okay? Sometimes this standard normal curve, all right, standard normal curve has a nickname. The standard normal curve is simply called a z-curve because the numbers on the bottom are z-scores. So here's how I'm going to do this. Okay. I'm going to go second. I'm going to hit the vars button. And underneath the distribution menu, I'm going to choose the second option, normal CDF. Normal for a normal curve, C for cumulative, DF for density function. Normal cumulative density function, because we're adding up a whole bunch of area. That's why it's cumulative. So we're going to choose that option. So let's look at this first one. It says, what's your lower and upper bound of your shaded region that you care about? Well, this actually starts way back to the left. Remember, these go on forever. So it starts at negative infinity. But I can't enter in negative infinity, but I can enter negative and put a whole bunch of 9s in there. That's like negative infinity. What's the upper boundary? What z-score are you going up until? You're going up to 2.85. Okay, on a standard normal curve, the mean is 0 and the standard deviation is 1, so we leave those alone. So if I hit paste and then I hit enter, what do you know? 0.9978. What did we get here? 0.9978. Okay. Look at the second option here. What did we want to find? We wanted to find z is greater than negative 1.66, so we tried to find this green region. The nice part about the calculator doesn't care about left tail and right tail. So let's go back under normal CDF. Let's start at negative 1.66 as our lower bound. And how far does this go to the right? Well, it goes out to positive infinity. Can't put positive infinity, so we put a bunch of 9s. And we leave the 0 and the 1 alone. Paste. There we go, 0.9515. What did we get from the table? 0.9515. This is just a lot quicker. Okay. The next one, we're trying to get this blue area from a z-score of 2.46 to a z-score out to infinity. Okay. So we're going to go from 2.46 out to infinity. 0.0069. 0.0069. You can even do it between two z values. Okay. On the last question, we're going from a z value of negative 1.27. That's where we're starting our shading. And we're stopping our shading at a z-score of 0.89. What do you know? That's 0.7112. Okay. Now the table told me 0.7113. That's close enough. Okay, this is exact. This is an estimate. Tables just give us estimates. So you can read this on your own, how to solve problems involving normal distributions. I'm just going to walk you through it. Okay, so let's do a few examples. So this first example, it says, on the driving range, Jordan Spieth practices swing with a particular club, hitting many, many balls. When Spieth hits his driver, the distance the ball travels follows a normal distribution, okay, with a mean of 305 and a standard deviation of 8 yards. Okay? It says, what percent of Spieth drives travel at least 290 yards? What does this mean? It means 290 yards or more. So if we were to draw this, we would draw a normal curve. Okay, so we're going to draw a normal curve. What value goes down the center? Well, 305 does. Okay, 305 does. And I'm going to tell the reader Jordan Spieth has a normal driving curve, and his mean is 305, and his standard deviation is 8 yards. Okay. We want to know how many of his drives travel at least 290. Well, 290 is to the left of 305. Okay. It's to the left of it. So if I put 290 here, okay, what does at least mean? 290 or more. Okay. So what we're really looking for is we're looking for that shaded part of the graph. Okay. All right, and let's let x equal Spieth's driving distance. We really should give that variable a name, so I'm just calling it x. And I'm going to tell the reader x is distributed in normal fashion. And so what are we looking for? We're looking for the probability that Spieth's driving distance, which we're calling x, is greater than or equal to 290 yards. Well, to be able to use the tables, I would have to turn these into z-scores. So how could we find the z-score for 290? Well, we would do 290 minus the mean, which is 305, and divide it by the standard deviation, which is 8. So that would give me negative 15 over 8. Right? And as a decimal, I think I know what that is. I think it's negative 1.875, but I'm going to check. Negative 15 divided by 8. What do you notice? I'm right. Negative 1.875. So if you turn these distances, okay, these are like x values. These are the values of the variable. Okay, but we should turn these into z-scores if we want to use the table. So the mean, if you put in 305 here, that part would be 0, and 0 over 8 would still be 0. So the mean always has a z-score of 0. And we said that this value has a mean of, or has a z-score of negative 1.875. Okay. So I'm going to show you how to do this two ways. Okay. I'm going to show you how to do this two ways. So to find the probability that the variable is greater than 290 is the same thing as saying find the probability that the z-score is greater or equal to negative 1.875. These mean the same thing. This is a variable value, and we turn the variable value into a z-score. All right, so if I go to my tables, okay, remember the tables give you a left area, not a right area. But if I go to negative 1.87, here is negative 1.87, and here's negative 1.88. All right, so the best thing we can do is to find negative 1.875 is to take the average of those two. Okay, so about 0.0304. Okay, so this part of the curve, okay, that part of the curve to the left has an area of 0.0304. But we're trying to find the right area. So how do we do that? We would have to take 1 minus, because both of these combine to give you 1. So if you just want to find this red shaded part, you would take 1 minus this. So 1 minus 0.0304. And the estimate we would get would be about 0.9696. So 96.96% of Jordan Spieth drives travel at least 290 yards. Now let me tell you about the beauty of the calculator. We had to do all this work to convert to z-scores. The truth is we really didn't have to. Let me show you. All right. When you use the calculator, it will do all that conversion automatically for you if you know how to do it. So go back under the distributions menu, go to normal CDF. But instead of using z-scores, let me just put in the z-score again. So negative 1.875, and this curve goes out to infinity, positive infinity. If you leave, mu is 0 and sigma is 1. So I hit enter, and my answer is about 0.9696. Well, you notice it's exactly the same thing. But let me do this a different way, the same problem a different way. Instead of putting in z-scores here, remember z-scores have to have 0 and 1 there. Instead of putting z-scores, let's put the actual numbers. So where we start the shading is 290, but we never stop the shading. It keeps going on to infinity. So I leave that as infinity. But instead of 0 and 1 for a standard normal curve, let's just use this particular normal curve. So on this particular normal curve, the mean was 305. What was the standard deviation? It was 8. So before I hit paste, what the calculator is going to do is going to take this 290 and it's going to convert it to this z-score of negative 1.875 automatically for us. Then it's going to look, the calculator is going to look into its own internal memory and do the calculation. So what do you notice? It's exactly the same, 0.9696. So if you use the calculator, you don't even have to convert to z-scores. All right? But what is important for you to get full credit on the AP test, here's what you got to do. You have to give the variable some sort of name, some letter name like x. You got to write that the distribution is normal. So you have to say x arrow, normal curve, give the parameters, tell the mean and tell the standard deviation. You should draw a picture and shade the appropriate parts. Okay? And you should write some sort of probability statement. What are you asked to find? The probability that Spieth drives are greater than 290. And then you could simply write the answer. So all of this stuff right here, this is actually not necessary. All of this stuff is not necessary. It's not necessary to write the z-scores. Now, let's do part B, but let's do it just the easy way. All right, so let's make a picture. We've already told the reader what x was, so we don't have to redefine that. Okay, but we should still say that x is a normal distribution again. So we're going to draw the curve again. The mean is 305 still. The mean hasn't changed. What we want to know now is what percent of Spieth's drives travel between 305 and 325. Could I convert these to z-scores and do it the hard way? I could. I really don't see why you would do that though. It's extra work. So what are we looking for? We're looking for the probability that Spieth's drives, which we're calling x, is between 325 yards and 305 yards. Let the calculator do the work for us. Let's go back under our distributions, normal CDF. The lower boundary of the shading is 305. the upper boundary of the shading is 325. The mean is 305, and the standard deviation is 8. So all we have to do there is type in that info and hit enter. 0.4938 if I round. 0.4938. And sometimes it's good if you write a short little sentence. So say something like this, 49.3, this is a probability and I can express it as a percent. This number should never be bigger than 1. It should never be smaller than 0. This area right here is a decimal. 49.38% of Spieth's drives travel between 305 and 325 yards. I mean, if this, remember the standard deviation was about 8. So if I go, 20, if you did convert these to z-scores, that would have a z-score of 0. And if I'm going 20 units and I have a standard deviation of 8, 20 divided by 8 is 2.5. So that would have a z-score of 2.5. So to find that the hard way in a table, you would find this area in black, find the area to the left of the z-score of 2.5, and subtract off that area, which would be 50%. And then you would get the red area. The black minus the blue would be the red. Easy ways and hard ways. I suggest easy ways. All right, let's do another one. Said high levels of cholesterol in the blood increase the risk of heart disease. For 14-year-old boys, the distribution of blood cholesterol is approximately normal, with mean of 170 and standard deviation of 30. What is the first quartile of the distribution of the blood cholesterol? So let's define a couple things to make this problem easier. Let's let y equal the blood cholesterol of 14-year-old boys, based on what it told me in the problem. Measured in milligrams per deciliter. Okay, so I defined a variable. Okay. Now what does it tell me? It tells me that this variable is approximately normal. So y is a normal variable, okay, that has a mean of 170. I don't have to put units again because I did right there. All right, and a standard deviation or a sigma of 30. Again, I don't have to write units again because I have it right there. Now let's draw the picture. So it's a normal curve, so I'm going to draw a normal curve. And if I'm just dealing with x values, okay, then 170 would go in the middle. Okay. But what is this question asking about? They want to know what's the first quartile. Well, what's our knowledge about quartiles? What does it mean to be first quartile? We say that's Q1. But what is Q1? It happens to be the 25th percentile. Okay, it's the 25th percentile. Well, what does that mean on a normal curve? Okay, there's some x value down here. I'm just going to call it x, where if I look at the area, that area needs to be 25%. So I'm looking for the x value that would give me an area of 25%. Okay. How in the heck do we do that? Well, obviously, just the way I drew this x value, well, if half the curve would be 50%. So this value right here has to have a negative z-score because it's to the left of the mean. So let's look at our table here, okay? But this one's a little different. We're given an area instead of asked to find the area. So we have to look inside the table for the number that's closest to 0.25, okay? So as I start to look down here, I'm going across, all right? We need to pick the number that's closest to 0.25. So to me, there's not a number that's exactly 0.25, but there's two numbers that are really close to 0.25. All right, so these two numbers are, it's about 0.25 would probably be about halfway in between each of these, because it's 17 hundredths or 17, what is that, 10 thousandths away from this number, and it's 14 10 thousandths away from that number. Okay, so if I think about it, it's probably in between those two numbers. So we should probably just average those two numbers. What's the z-score for the 25th percentile? Well, that's negative 0.6. And if we go halfway in between 0.07 and 0.08, the z-score is negative 0.675 approximately. Okay, so you have to look in the table because these are the areas. Inside the table is the areas. On the outsides are the z-scores. So we just figured out what the z-score was. It's negative 0.6, and that's halfway in between 0.7 and 0.8. So I'm estimating the z-score is negative 0.675. So what did I just find? Did I find an x? No, I found the z-score. Okay, I found the z-score. The z-score is negative 0.675. So how in the heck can I figure out what the x value is? We'll go back to the z formula. Okay, the z formula says you take your x value minus your mean and divide by your standard deviation. Well, we know the z-score, that's negative 0.675 approximately. We don't know the x value, but we do know the mean is 170. Now, do we know the standard deviation? We sure do. The standard deviation is 30. Okay, so how do we solve this? Well, we use our arithmetic skills. Take negative 0.675, set this up as a proportion, and multiply it times 30. So negative 0.675 times 30. Well, that's negative 20.25. Okay. If I take 1 times this whole x minus 170, it's still x minus 170. Now, how would you solve for x? We would add 170 to both sides. So x would have to equal, take this number plus 170, and you get 149.75 milligrams per deciliter. So that is the proper number, 149.75. So a boy that has a cholesterol of 149.75 is the value of the 25th percentile. That is the absolute hardest way to do this. Here's the easy way. All right, in your calculator, go under your distributions menu. But if you are given an area, instead of using normal CDF, we use this thing called inverse normal. And now it's asking you for a couple things. It's saying, okay, what's the area? Well, this area right here is 0.25. Okay. Down here, it's saying, is it a left area, a center area, or a right area? Well, it's a left area. I always like to do it from a left area, by the way. All right. But what's the mean? What's the mean in x values? Well, it's 170. So we can type in 170. What's the standard deviation? It's 30. If I hit paste, what do you notice? 149.765. really, really close. This was our estimate. The calculator did it at once. Notice, you didn't have to find the x value. All right, this is the hard way to do it. Use inverse normal when you need to find an x value. So let me make a note. You might want to make this in your notes. So we're going to use inverse normal when we need an x value. When did we use normal CDF? We use normal CDF when we need an area. Okay, so those are the difference between the commands and the calculator. So let's look at the next problem. It says, here are the lengths in feet of 33 great white sharks. Okay, so let's go ahead and start to put the data into our calculator here. All right, clear some data here. All right, I should have done this ahead of time, sorry guys. 18.7, 16.3, 18.6, 16.4, 15.7, I'm going across, 18.3, 19.6, 17.8, 15.9, 17.6, 15.1, 16.4, 16.7, 17.8, 16.2, 15.6, 17.8, 13.8, 12.2, 15.2, 15.7, 12.4, 19.1, 16.2, 22.8, 16.8, 13.6, 13.2, 15.7, 19.7, 18.7, 14.2, 16.8. That's the last data value. I have all 33 of them. So it says plot the data by using a dot plot, a stem plot, or a histogram. So it's up to you which one you want to do. I'm just going to choose to make it histogram. Okay. If you wanted to make a dot plot or a stem plot, okay, you might want to sort your data. If you remember how to do that, stat, sort, ascending, list one. Okay. So I go stat, go back to your list, and the data should be sorted for you from smallest to biggest. Okay. Actually, I'm going to take that back. I'm going to do a stem plot or a stem and leaf plot here. All right. So stem and leaf. So my stem is going to be the whole number, and my leaf is going to be the decimal. All right. So if I look at my data here, when I start writing this down here, all right, the smallest shark was 12.2. So there we go, 12.2. And if I keep going, I have one that's 12.4. Right. And then I have 13.2, 13.6, 13.8. Then I have 14.2. I have 15.1, 15.2, 15.6, 3 15.7s, 1 15.9, I have 2 16.2s, I have 1 16.3, 2 16.4s, 1 16.7, I have 2 16.8s, I have a 17.6, I have 3 17.8s, I have an 18.3. I have an 18.6. Two 18.7s. I have a 19.1, a 19.6, a 19.7. Okay. I don't have any 20s. I don't have any 21s. But I do have a 22.8. Now remember, a stem plot or a stem and leaf plot is like a histogram on its side. So these are like bins. So there's 2 sharks in the 12 feet range, 3 sharks in the 13, 1 shark in the 14, a whole bunch of sharks in the 15, 1, 2, 3, 4, 5, 6, 7. All right, 8 sharks in the 16-foot range, 4 sharks in the 17-foot range, 4 sharks in the 18-foot range, 3 sharks in the 19-foot range, no sharks in the 20, no sharks in the 21, 1 shark in the 22. It's like a histogram on its side. But on the stem plot, to get full credit, give it a title, lengths of a sample of 33 great white sharks. Okay, so give it a name, that's a title, and then give a key. So tell the reader that 12.2 equals 12.2 feet with units. So that's your key. Okay, title, key, needed for full credit. It says, check whether it follows the empirical rule. Okay. Well, what's the empirical rule? That's the 68 within 1 standard deviation, 95 within 2 standard deviations, and 99.7 within 3 standard deviations. All right. These are percents. So how can we find the mean of this data? What's the mean of this data? Well, I already have the data in list 1. Actually, let's not call it mu because it's a sample. Let's call it x bar. So if I run one variable stats, stat, calculate, one variable stats for list 1, calculate, there's my mean, 16.564 feet. That's the mean. What's the standard deviation? Okay. Well, should I use S or sigma? Well, let's say this wasn't a sample. Okay, lengths of 33 great white sharks. Let's just say it was the population. Well, if it's population, let's use sigma instead, and let's call that mu. All right, so sigma here is 2.230. Okay. So if this distribution, first off, does it look normal? Does it look like a bell curve? Not really. So my first thought, the answer is no. Okay, but we have to do calculations to show it. All right. So if we take the mean, 16.564, all right, if this is a normal distribution, that number would go in the center. All right. And if it was a normal distribution, if I went out 1 standard deviation each way, then 68% of the values, about 68% of the values should be between those two numbers, whatever they are. So let's go 16.564 plus or minus 1 standard deviation, and a standard deviation is equal to 2.230 feet. Okay. So if I think about the low side here and the high side, if I subtract those two numbers, what is 16.564 minus 2.230? 14.334. And so this number would be 14.334. And then if I added 16.564 to 2.230, we would get 18.794. So this number here is 18.794. Let's look at our data and figure out how many of those sharks are between these lengths. Okay? And let's circle them when we get them. So where's the first one that's above 14.33? Well, that one is. We're going to keep going until we don't go over 18.794. Okay, so circle all these that are less than 18.794. Okay. So those are the values that are within one standard deviation. How many values are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So 23 of the sharks out of 33 of the sharks are between these numbers. So if I do 23 divided by 33, that amounts to 69.70%. Well, this number, it's close to this, but it's a little bit different. It's a little bit off. Okay, let's see how much the next one is off. Well, how would we do the next one? We would take our mean, and then you would plus or minus 2 standard deviations. So 2 times 2.230 feet. So if I did this real quick, I would just do 16.564 minus 2 times 2 point, whatever that number was, 230. 12.104. So the lower number here would be 12.104. And the higher number here, all we got to do is enter this again and change that minus to a plus. 21.024. Okay. So these numbers in red, there were 23 numbers I already circled that were within 1 standard deviation. Those numbers are also going to be within 2 standard deviations. So circle all the numbers that are bigger than 12.104, and the numbers less than 21.024. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. I can't include this one though. So on this one, there's 32 out of the 33 are within 2 standard deviations. And 32 divided by 33 is 96.97%. All right, this number is not 95, so it's slightly off. And what about if we go out to 3 standard deviations? 16.564 plus or minus 3 times 2.230. Do the bottom one first. If this curve was normal. All right. It would go down to 9.874, and it would go up to 23.254. All right, so these numbers go from 9.874 to 23.254. Well, all of these numbers I circled so far are bigger than 9.874. Can I include this one now? Can I include the 22.8? Is that in between these two numbers? Yes, it is. So when I do that, I've circled everything. So that's all the data. All the data falls within 3 standard deviations. So 33 divided by 33 is 1, which means 100%. So this number is bigger than that number. So although these numbers are close, it's close to normal. It's not exactly number. Okay, so it's close. Data is close to normal, but not exactly normal. Okay, this number relatively close to 68%. This number relatively close to 95%. This number relatively close to 99.7%. So it's close, and if I look at the histogram, it kind of has that kind of a little bit, it kind of goes up and down, but then it goes back up, and it kind of comes back down. So it's close to normal. It's close to bell-shaped, but it's not exactly bell-shaped. Okay. So it's close, but not exact. Okay. And that is where we are going to stop this video. So hopefully the explanations helped. Sorry about the length. It's really important that you understand these concepts and the applications of these concepts. So hope the information was useful, and if you have any questions about it, just ask in class or ask any math teacher.